Okay, question 8. Table 8.1 shows some data relating to the properties of air, gel, and body tissue. The data are given to 3 significant figures. Okay, so what I have written, as you can see, what is written there, it's me, what I have done. I've done that so that we don't waste time when we are doing things where I have to continuously be writing. Show that the specific acoustic impedance of gel is 1.68 times 10 to the power of 6. So acoustic impedance is represented by the letter Z. Is found by using the density of the material multiplied by the speed of ultrasound in that medium. So if you check out here, for gel, we are given the density. We are also given the speed of sound in that medium, which is 1.4. So here we multiplied 1.2 times 1.4. This gives us the specific acoustic impedance of gel. Then the next question says complete table 8.1 by calculating the missing values to 3 significant figures. Use the space below for any working. Obviously, we want to find this value for air, but it's just a waste of time. Why? Because to find density for air, we would have to take the formula again. I've already worked it out, but for me, it's just to show you what to do. Density is equal to specific acoustic impedance divided by the speed. Now we are given the specific acoustic impedance as 440, the speed is 340. Likewise, if we have to find here the speed of sound in the tissue, we are given the density and the specific acoustic impedance, so the speed of sound will be equal to specific acoustic impedance divided by density. So that's what we have to do there, and then we write it as I have already written it, as you can see. Okay, so next, use the information in A to calculate the intensity reflection coefficient. Now the intensity reflection coefficient is represented by alpha. Alpha in this case represents the intensity reflection coefficient. Ultimately, the intensity reflection coefficient is simply telling you the ratio of the wave that was reflected over that was transmitted. So in other words, alpha can be said to be IR over IT. So we are talking about the intensity of the light, of the intensity of the wave reflected IR over the intensity of the wave transmitted IT. Okay. So use the information in A to calculate the intensity reflection coefficient for an air tissue boundary. So alpha is equals to Z1 minus Z2. What does Z1 minus Z2 represent? Alpha, remember I told you that is the ratio of the reflected intensity over the transmitted intensity. However, if you have the transmitted intensity and the reflected intensity, you can calculate alpha like that. But in this case, we want for the air tissue boundary. So we have to use the acoustic impedance for air, the acoustic impedance for tissue, the acoustic impedance for air, the acoustic impedance for tissue, whatever order you do. But of course, it will be mathematically better to use the bigger one minus the smaller one anyway. So it's air tissue. So this is the acoustic impedance, the acoustic impedance. So as you can see, that's what I do here. 1.6 million 80,000 minus 440 over the same plus 440 squared. This gives us 0.999999. That's the ratio of the intensity that is reflected over the intensity that is transmitted. In fact, this is not transmitted intensity, sorry. This is the incident intensity. Let me erase this part. It's actually the incident intensity. It's actually the incident intensity. So let me give it the letter I naught. That's not the transmitted, it's incident intensity. I'll show the relevance. No harm has been done there. Then they want also the specific acoustic impedance between the gel and the tissue. So the intensity reflection coefficient. So between the gel and the tissue, they have equal acoustic impedances. So as you can see, it is this minus this over this plus this. It is not proper of me to put the combined square, but because mathematically it's not correct actually. So let me remove what I put there. Sorry. Let me remove what I put there, because it's not correct mathematically. So then this becomes this squared separately. Okay, so this gives us an acoustic impedance of 0. The intensity reflection coefficient of 0. Then the final question says, use your answers in B to explain why gel is applied to the skin during ultrasound scanning. Why do we apply gel to the skin during ultrasound scanning? Now, the answer lies in this point, which I told you, the alpha, the intensity reflection coefficient. Alpha, remember, and we are supposed to use this information, the one we got as 0.99 between the tissue and the air, the other one between the tissue and the gel. The reflected intensity over incident intensity. Now, here's the thing. The incident intensity, we can assume that it's 100% because that's the intensity of the wave as it arrives on a boundary between two media. So, for example, the boundary between air and the tissue. So that's I naught. IR is the fraction or the part of that intensity that is reflected. So it is apparent that IR can never be greater than I naught because IR is simply a part of I naught. So when we get IR over I naught as 0.999, which is approximately, if we round off here, this will become 1. Even if, let us deal with it from there. It means that we can say IR, if I multiply both sides by I naught, is equal to 0.999 of I naught. So in other words, IR, if it is 0.9999 of I naught, it means that IR and I naught are not that different, because 0.999, if you round it off, becomes 1, meaning that IR will be equal to I naught. So the reflected intensity is almost equal, considering 0.999, to the incident intensity if there is an air tissue boundary. Now, what does that mean? It means that most of the intensity, most of the ultrasound wave is being reflected. This is the short story of it. But if IR over I naught is equal to 0, so what does that mean? Let me multiply both sides by I naught. Then this will become 0. So it means that the reflected intensity is equal to 0, meaning that the entire incident wave I naught is being transmitted. If IR, the reflected one, is 0, all of it has been transmitted. So that is the implication of alpha being 0. So alpha being 0 means that the entire, or alpha being 0 or alpha being near 0. Near 0 in this case is not 0.999 because actually it starts, the scale is from 0 to 1. So 0.999 is close to 1, whilst, for example, 0.00001 is close to 0. So when alpha is 0 or close to 0, it means that most of the intensity is being transmitted into the other medium. So between gel and tissue, then whatever is in the gel is able to go into the tissue 100%. So these are the implications of those values. So let's come to the question. Use your answers in B to explain why gel is applied to the skin between the ultrasound scanning. So I'll read my answer and try to use what we have just said. Without gel, as we saw, almost all of the incident ultrasound is reflected from the skin. Yes, you have your ultrasound machine which you are putting in contact with the skin, but whatever contact we put, in a real sense, there is always a layer of air between the skin and the ultrasound machine, meaning that ultrasound they have to first go through that thin layer of air before they go into the skin. Now, the fact that they go through the air and then they try to go through the skin, then there's an air tissue boundary, which means that most of the ultrasound are reflected back. So to encounter this, what do? We put a gel. The thing about the gel is that for the most part, it's air, like oil, it's an air seal in the sense that air cannot really enter into the gel. So once the gel is the one that is the layer between the ultrasound machine and the skin, ultrasounds are just leaving the machine, going through the gel, and then going through the skin. Why? Because the gel has an acoustic impedance approximately equal to the acoustic impedance of the skin. As a result, alpha is 0. None of the incident waves are reflected. So there must be a gel if we want to ensure that none of the incident waves are reflected back.